Hey, welcome back. It's Kevin again. Let's talk about layer 4 of the OSI model. Just as a review, we've already talked about layer 1, the physical layer, layer 2, the data link layer, layer 3, the network layer. Now it's time for layer 4, the transport layer. At the transport layer, we want to focus on 3 primary things. Number 1, the protocols, some of the protocols that reside at layer 4. Number 2, we want to think about how windowing occurs with one of those protocols, specifically TCP, the Transmission Control Protocol. And finally, let's talk about buffering. We want to talk about these 3 main topics. TCP and UDP being the primary protocols at layer 4, how TCP can perform windowing, and how we can perform buffering. Let's start off with TCP and UDP, the Transmission Control Protocol and the User Datagram Protocol. These are 2 of our primary protocols up at layer 4. TCP is considered to be a connection-oriented protocol. In other words, it's reliable. If I send a segment, remember that's our layer 4 protocol data unit, a segment. If I send a segment, I should get an acknowledgement from the receiver that it got the segment. And if it didn't get the segment, I can then resend it. So we have some reliability. UDP, however, is considered to be a connection-less protocol. Connection-less meaning that there's no acknowledgement. When I send traffic, there's no acknowledgement from the far end that it got it. It's a fire and forget type of transmission. And you might wonder, why would we want to use something that's unreliable? Why would we not prefer to use TCP? Well, let's think about the header size. Let's think about the overhead of TCP versus UDP. Here's the header of a TCP segment, and in a moment when we compare it with the size of a UDP segment, you're going to see this is much larger. But what sorts of things do we have inside of a TCP segment header? Well, we have a source port and a destination port. Remember at layer 3 we had source and destination IP addresses typically? Well, here we have source and destination ports. And these ports point to upper layer protocols. For example, the Telnet protocol that would allow us to do remote terminal access. That's using a well-known port of 23. In fact, consider this example. We have a client wanting to communicate with a web server. The client has a source IP address, we'll say of 10.1.1.1, and we're sending a packet with a destination IP address of 172.16.1.2. That's the IP address of the web server. If we were to peer inside of the header, we would see not only source and destination IP address information, we would see source and destination port number information. Port numbers of 1023 and lower are referred to as well-known ports. There are assignments for many of those numbers in that range, where we know that Telnet, for example, typically uses port 23. We know that a web server using HTTP is going to be using port 80 most of the time. So when we send from the client to the web server, we're sending to a destination port of 80. That's included in the TCP header. But in order to get the traffic back to the client, we have to have a source port. Remember that I said ports 1023 and lower were well-known ports? What about our client? It doesn't have a well-known port. It's going to pick a port number in the range of 1024 and higher. It goes up to 60,000 and some. And these higher port numbers are called ephemeral ports. And notice we've randomly selected a port number of 1248 as our source port going to the web server. Then when we have return traffic coming back from the web server, it's sourced from port 80, that's the web server's port, and it's destined for the client's port, 1248 in our case. All right, back to the TCP header. What else do we have? We've got source and destination port numbers. We've got sequence numbers and acknowledgement numbers. Remember we said that when we send traffic, we're going to get an acknowledgement that it was received. Let's consider how this works. This uses something called TCP windowing, which, by the way, was another one of the 3 things we wanted to talk about. Let's go ahead and talk about it right now. With windowing, we can do something sometimes called a sliding window. A window represents how many bytes we send at one time before we wait to get an acknowledgement. If we're on a fairly reliable network, there are very few drops, then it's usually safe to send a bunch of bytes at one time and then wait for an acknowledgement. You see, if we just send a little bit and wait, a little bit and wait, we're spending a lot of time waiting. It's a very inefficient packet flow. So what we can do is use a sliding window with TCP to dynamically grow the window size. Notice on screen, we're starting out with a window size of 1, meaning I'm going to send one segment and I get an acknowledgement. I sent segment 1, the receiver acknowledges and says, okay, send segment 2. Because segment 1 got there successfully, I'm now going to send segment 2. And I'm going to send segment 3. You see, I doubled my window size. The receiver got them. The receiver said, send me segment 4. I doubled my window size again. I went from 1 to 2 to 4 segments in a single window. So I send segments 4, 5, 6, 7, and assuming that I continue to get acknowledgments, my window size can grow and grow and grow. I can start sending 8 segments, 16, 32, 64, 128, 256, 512, and on and on and on. The theoretical maximum number of bytes, not number of segments, but the number of bytes that you can send in a single window size is something over 2 billion bytes right now. So we can have really, really big windows, which is a good thing on a reliable network. That's how windowing works, and that's what the acknowledgement number has to do with in our header, and the sequence number can make sure that everything gets put back together in the correct order if we have load balancing going on. We've got some error correction in the form of a checksum, but overall, one of the big things I want you to notice about the TCP header is it's big compared to a UDP header. Here's the size of a UDP header. We still have source and destination port numbers. We've got an optional UDP checksum for error correction, but notice there's no acknowledgement. There's no windowing going on here. There's another field that says what the length of the segment is, but that's about it. It's a pretty stripped down header. Why would we ever want to use this? Because we're lacking acknowledgments. We're lacking any assurance that our traffic got there. Well, this is the reason, guys. It's low overhead. This is a beautiful solution for something like voice over IP. If I'm sending voice traffic encapsulated inside of an IP packet, I would much rather have a smaller header at layer 4. You see, my payload of my voice packet, depending on how I'm encoding it, it might be 20 bytes. Only 20 bytes of payload. My header size, even if I use UDP, if you add up the IP header and the UDP header and the RTP header, that's the voice protocol, that's 40 bytes. Already, the layer 3 and layer 4 protocols have headers that's twice the size of the payload. That's not a great ratio. So we definitely want to keep down the header where we can, and using UDP is a great option. And besides, if we dropped a voice packet, we wouldn't want to resend it anyway. It would sound silly to have a voice packet show up out of order, wouldn't it? So those are TCP and UDP, two of our most popular protocols up at layer 4. And we've already discussed what windowing is, and that leaves buffering. What do we mean by buffering? Well, imagine that traffic is coming into a router faster than it can be sent out. Maybe we're coming in from a relatively high-speed local area network, and we're going out a relatively low-speed wide area network. Well, because of that big speed mismatch, the router may be receiving traffic faster than it can send it out. What does it do with that excess traffic? Well, instead of just dropping it, what it's going to do, or what it can do, is allocate some memory called a queue or a buffer to store up those packets temporarily until the WAN bandwidth demand dies down, and then the router is going to be able to take those packets out of this waiting area, out of this buffer, and send them on the WAN. If we have continual congestion, however, if the bandwidth demand does not die down, that buffer is of a finite size. It's only going to hold so many packets, so it's possible that that buffer is going to fill all the way to the top and a newly arriving packet is going to be discarded. It's going to fall off the top of that buffer. By the way, there's a term for that. It's called tail drop. Tail drop happens when a packet tries to go into a buffer, but it's discarded because the buffer is full. But buffering, it can help us avoid packet drops when we have a speed mismatch. Those are three of the big things going on here at layer 4. And when we talked about layer 2 and layer 3, I showed you an actual device. I showed you a switch for layer 2. I showed you a router at layer 3. Don't really have anything to show you here at layer 4. There's not necessarily a layer 4 device, although I guess a router could be. A router could be a layer 4 device because it could make its forwarding decisions based on layer 4 information, not just layer 3 information, not just a destination IP address. It could make a decision based on a destination port number, as an example. So a router, I guess we could say, is a layer 3 and higher device. Same thing with multi-layer switches. A multi-layer switch is a switch that can at least route at layer 3, but it might be able to make other decisions as well at higher layers based on upper layer information. That's layer 4. We'll see you back next time for layer number 5, the session layer.